Hello, this is the senior design showcase for drone delivery team Black.
So an overview of this project. We have to design and create a drone that needs to deliver food to four corners of a soccer field in 20 minutes. The food needs to be delivered in a 3 meter radius. It needs to be able to have a max range of 2,000 feet. The drop needs to be independent. The payload must be undamaged as it's dropped, and the most deliveries by a team wins.
All right, for the chassis design selection, main objective is to secure and house all the drone's electrical and mechanical components. We have to pretty much select a really robust chassis because it has to house uh, various components like four electronic speed controllers, four brushless motors, four 6S batteries, payload mech, landing gear, and receiver. For our drone, we're doing a quadcopter setup, so four motors, four propellers, and an X-frame style. It's in our senior design 2 chassis design, we've used bonded layers of aerospace grade plywood and balsa wood, separated by mounting clamps for arm tubes and standoffs, separating each plate. So this is just a comparison of what our chassis looked like for our first senior design course in comparison to the revisions that we made for the second semester. And your key differences is improved strength to weight ratio, switching over to PLA printed to balsa wood and aerospace wood. We also decreased manufacturing costs and time because the 3D printed chassis would cost us a fortune, and with a 2-day lead time, this was just a valid substitution to go with. We PLA printed the motor mounts, landing gear, and arm mounts, and then we used carbon fiber tubes for the arm mounts as well as the landing gear tube as well. So for the delivery payload design, we have some key summary and requirements we'd like to discuss. So designing a payload delivery system is a vital component. It's mainly responsible for ensuring that the product designated for delivery arrives in the intended location in a safe and effective manner. So some functional requirements to having a good payload system is that the drone must be able to successfully complete a delivery for all four corners of a soccer pitch starting from midfield. Payload mechanism must be remotely operated and released, although manually loading is permitted in the midfield point. Each payload released within each corner of the soccer pitch has to be released within a 3 meter radius in order for it to deem successful, meaning a point added. Anything on any deliveries that are outside of the circle or damaged or dropped before the intended delivery location would not count. So upon selecting the payload design, we had three common choices that are in today's market, which is a winch and claw mountable container box with a trap door or quick release mechanism. After assessing the pros and cons for all three of these design choices, we went ahead and decided to go with a quick release mechanism. It's just a simple, lightweight, and a low-cost way to create this payload mechanism. So just to summarize what this means is that we made some revisions from Senior Design 1 over to Senior Design 2. These pictures pretty much just show the design implementations that we made, as this can be including extra filament, extra carbon fiber that we did in order to reinforce the plate in which the servo mount is mounted to. After conducting a static analysis, we decided to go with an MG995R servo motor. It's theoretically proving to generate enough sliding force along the axis of the push rod, which is generated about 5.32 newtons, which will overcome the static coefficient of friction normal forces of 4.905 newtons. Key upgrades is higher stall torque, increased payload push rod diameter for increased stiffness and robustness, and an additional linkage for increased reliability and smoother movement, and additional support material, just like mentioned before, to add further strength and to secure the servo motor in place. And this is just what our final payload design is going to look like for Senior Design 2.
For the electronics, we went with a Pixhawk 6X Mini flight controller. The onboard sensors for the flight controller include an accelerometer, gyrometer, a barometer, and a magnometer. It's a 6-axis IMU. So it accounts for the pitch and yaw of the drone. For the ESCs, for all 4 of our motors, we use the ZTW Beetle Series 50A, 60A brushless ESC. And we found those in the inventory, and of all the options, they work the best with the motors that we had. And to link the ESCs with the flight controller, we used a power distribution board, the Hollybro, which was compatible with the Pixhawk 6X Mini. It works well with all the motors and the ESCs, and it's 50 by 50 millimeters, so it fits easily on the drone's chassis on the top. And that's where we're going to put all the electronics.
So for our transmitter, we're using a FS I6 transmitter, and for the receiver, we're using an IA6 receiver, and the IA6 receiver uses PWM communications, and what we're gonna use, the flight controller uses PPM communication, and we're using a PPM encoder to transform the PWM to PPM communication, which also reduces wiring. For our ground control station, we're using Mission Planner, and it's an open source software that lets us calibrate and code the drone, as well as giving us telemetry during our mission time.
We utilized eCalc to find a battery that would work for our motor and propeller selections. The one that we found was called the HRB 6000 milliamp hour 6S LiPo battery. And we're going to be using 4 of them for a total of 24,000 milliamp hours. Each of them is 6 cells and about 1.78 pounds. So all 4 together would be around 7 pounds. And even though eCalc helped us find our battery and did the calculations for us, we still wanted to understand why this battery was selected and provide or prove its compatibility with our calculations. So in order to do this, we use the max current draw and the minimum flight time provided by eCalc. To figure out which battery to use, we started by converting our minimum flight time from 6.8 minutes, which is on the eCalc, which will be shown later, to hours, which is 0.113 hours. We then calculated the total max current draw from all 4 motors by multiplying the max continuous current draw, which is about 60 amps by 4 for the 4 motors, to get a total current of 240 amps. After this, we calculated the power consumption of all 4 motors by multiplying the 240 amp current by the voltage, which is 22.2 volts, which got us 5,328 watts. And from here, we calculated the average power consumption over the flight time, which is just the watts, which was the 5,328 by the 0.113 hours to get our 602 watt hours. And then finally, multiplying that by the milliamps and multiplying it by 1,000 to give us a total of 27,120 milliamp hours, which justifies our choice of this 6,000 milliamp hour battery and using 4 of them in parallel for this drone.
So for our propeller, we chose the APC Propellers 14 by 5.5 multi-rotor propeller. We chose this propeller by using our APC performance data to determine a propeller that would generate heavy lift for our drone. It has a large diameter of 14 inches and a pitch of 5.5. Our drone weighs 13.5 pounds, including the payload. So to meet a 2-to-1 thrust to weight ratio, we need 27 pounds worth of thrust across the propellers. We evaluated the propeller at 10,000 RPM since our initial motor choice had a KV rating of 450, which would go up to 10,000 RPM. In completely static conditions, 4 of these propellers generate 45 pounds of thrust. Choosing a propeller that would create extra thrust gave us room for the fact that this data is based on completely static and perfect conditions, and the additional weight we'd acquire from the hardware is added in the building process that cannot be precisely estimated, which backs our propeller selection for our project.
Good enough.
The Sunny Sky X3520 was chosen because it was the most compatible motor in the senior design inventory for the propellers that we had already chosen and ordered. This motor could reach up to 11,544 RPM, and it's relatively large for a drone size. A wider stator produces more torque, so this was a good choice with its diameter of 35 millimeters. A taller stator is more efficient at the high RPM we'd be reaching, so the 20 millimeter height was also optimal among our options. After looking at a few other motors with the propellers, we found this one to be the best balance between RPM and torque that we could get in the inventory. So we performed thrust testing with this motor and our 14 by 5.5 propeller, and a single configuration created 9 pounds of thrust and drew a max current of 50 amps. So 4 of these would generate 36 pounds of thrust and meet our 2-to-1 thrust to weight ratio, and it would be compatible with our ESCs. And the thrust testing will be shown later in this video.